VLSos here. This is a video lesson on sigma notation. I'm going to start with something that we're going to analyze. 2 plus 5 plus 8 plus 11, which continues a pattern until we end with plus 59. What is this? It's a sequence of numbers, 2, 5, 8, 11. It doesn't go on forever. It ends with 59. But we're not just listing the numbers, we're adding them together. So we can call this a series. It's the sum of a sequence. This sequence of numbers has a pattern. We start with 2, we add 3 to get 5, we add 3 again to get 8. This series is arithmetic because the rule that generates the term values involves adding a constant difference, in this case, positive 3. We have a symbol to stand for the initial term value. T sub 1, the value of the first term, is equal to 2. And we have a symbol to stand for the value of the nth term, T sub n. We can find an equation or a formula to find the values of any position number n. And in this case, that is the value of the initial term 2 plus multiples of the constant difference, or 3 times n minus 1. We subtract 1 from n because we don't add the constant difference to the initial term. So how many terms are there in this series? The ellipses are used because we don't list them all, or we haven't listed them all in the paper here. We've taken a shortcut and had the ellipses stand for many unrepresented terms. But we know the pattern, so we're able to find those term values if we needed them. How many do we have? Well, if we assign the formula to find the value of the nth term to the value of the last term and solve it for n, then we'll find the position number of that last value of 59. So I'm going to do that by subtracting 2 from both sides. Then dividing by 3. And finally adding 1 to get n by itself. Finding n is equal to 20 has shown us that there is 20 terms in total in this series. And the value of the 20th term, the last term, or t sub 20, is equal to 59. So we found much important information about this series, but the series stands for a sum. In this case, we can think of the series, or any series, as the sum of terms, t sub n. And in this case, we want all the term values in a range from n is equal to 1 to 20. We have a way of representing series with notation because it can be difficult to write down the entirety of a series. And some series might have hundreds and hundreds of terms. So we have an efficient way of writing down all of the important information of a series. And that makes use of what we call sigma notation. I'll provide an example with this series. Sigma notation starts with the Greek letter S, which looks like an angular E. This is a capital S in the Greek alphabet. And we call this symbol sigma. Sigma stands for sum. It's a Greek letter S because it stands for sum. And what we add together belongs to the right of this symbol. If we're going to use sigma notation to stand for this series, then what we're adding together are term values. And those term values of this series is generated by this equation. So what we're going to add together are term values created by the equation 2 plus 3 times n minus 1. we're going to use this equation 20 times. We have 20 term values to generate with this sigma notation, which is an algorithm or a process for generating term values. But that process has a starting place and a stopping place. The first value that we're going to create has an n value of 1. And we put that starting value at the bottom of the sigma letter. This is called the lower bound. The variable n is used, and its beginning or first value is 1. And we're going to use all integer values up to and including 20. 20 is the stopping value or the final value that will be used. So we put that at the top of the sigma letter. This completes sigma notation. Sigma notation stands for a series. It doesn't calculate the sum. It's not an equation. It's a way of packaging the necessary information to generate the series. And I'll show how we use this to then create the series. This sigma notation has pieces. The equation that we use to calculate values is called the argument. And in this case, the argument is 2 plus 3 times n minus 1. The values of the variables that we use in the argument is a range of integer values. In this case, n is equal 1 to 20. And we put the starting value at the bottom and the ending value at the top. And together, we call this the index of the sigma algorithm. And the letter itself is just a visual clue that we're using sigma notation. So we call this letter sigma. How is it used? This represents a series. In this case, we took the series and we thought of it in sigma notation. But very often, sigma notation is your starting place. And then you would produce the series from the sigma notation. How do you do that? Well, this sigma notation is going to equal values of the series that are produced by it. You produce the first value of the series by starting with your lower bound in the index, the value that is at the bottom of the sigma. In this case, it's 1. And we would put that value into the equation and do the math and simplify to create the value of the first term of the series. You get the next term of the series by putting the next highest integer value. We've used 1. The next integer value to use above it is 2. So we put 2 into our argument, simplify and do the math, and in this case, it would produce the next value in the series of 5. Then we go to our next integer value. We just used 2, so the next value to use is 3. Put 3 into the argument, do the math, and it would simplify and produce the term 8. And we would continue to do that with integer values counting up until we got to the final upper bound value and use it. In this case, we would end by putting 20 into the argument, simplifying, and it would produce that final value in the series of 59. So the sigma notation stands for a process. And we can go through the process in order to generate the series. When we do, the series that the sigma notation generates is called the expansion. And the expansion then can produce a sum. We could literally add all of these numbers or use technology and enter the sigma notation or the series and add them all up. In this case, the sum would be 620. So the sigma notation doesn't directly calculate the sum like an equation would, The sigma notation stands for a series that you can use and expand. Let's get another example. In this case, we're going to start with sigma notation. We'd say sigma, or the sum, of -5 plus 13t, where the values of t start at 1 and go up by integer values until 10. This is sigma notation, and it stands for a series. We can form the expansion by starting with our lower bound value, integer value of 1, putting it into our argument or expression that uses that value, doing the math and simplifying. In this case, 13 times 1 plus -5 would make the first term value in the expansion of 8. The next value would be putting 2 in. 2 times 13 plus -5 makes 21. We'd put the next value 3 into the argument, do the math, simplify, and produce the value of 34. And we'd continue to do this, counting up in our index by integer values until we got to 10. If we use 10 times 13 is 130, plus -5 has a final value in the expansion of 125. The sigma notation produces the series, but we have yet to produce a sum to add up all of these terms. We can rely on the equation for the sum of an arithmetic series. In this case, S sub n will remind us that the equation is n number of terms divided by 2 times the value of the initial term plus the value of the nth term. And in this case, if n is 10, we're going to sum together 10 terms. It'll be 10 divided by 2 times the value of the initial term, 8, plus the value of the 10th term, we've already calculated to be 125. Or 5 times 133 will produce the sum of 665. Sigma notation is a way to package series. And series can have many terms, hundreds of terms. So very often a series requires a very efficient way of packaging it so it can be written down. And the sigma notation doesn't just package a series, it can also be used to expand and produce that series if you need it to find a sum. One last thing to say about sigma notation: the index, the starting and stopping values that are used for the variable in the argument, the index must be integers. You can't choose your values in the index to be fractions or decimals or anything other than integers. You can have negative integers, you can use 0, but the sigma algorithm requires that you start at an integer value and you go up by 1 until you get to your final integer value. It doesn't make sense to use sigma if you're not using it that way.